Hydrogen. You hear about it all the time, right? It's talked about as this cornerstone for a net zero future, a super clean, versatile fuel for all the hard to decarbonize stuff. But here's the thing, the real story of hydrogen is way more colorful than you might think.
Yeah, we've all heard the pitch, hydrogen is the ultimate clean fuel. You use it, and the only thing that comes out is water. Sounds perfect. But the multi-trillion-dollar question is, how do we make it in the first place? And is that process always as clean as we're led to believe?
Well, here's the kind of dirty secret of the industry. Right now, the overwhelming majority of hydrogen we make, we're talking over 75% of the 75 million tons produced every year, is what's called gray hydrogen. It's made with a process called steam methane reforming. You take natural gas, you react it with steam to rip the hydrogen atoms off, but it vents a truly massive amount of CO2 straight into the atmosphere.
And when I say massive, I really mean it. For every single kilogram of gray hydrogen that's produced, a staggering 9 to 12 kilograms of CO2 equivalent are released into the air. Let that sink in. That is not a clean fuel by any stretch of the imagination. So you can see why the entire industry is racing to find a better way.
Now, this race has pretty much given us two main frontrunners that you've probably heard about, blue hydrogen and green hydrogen, and they represent two totally different philosophies on how to clean up this process. So on one side, you have blue hydrogen. You can think of it as gray hydrogen, but with a cleanup step. It uses that same natural gas process, but it tries to capture the CO2 byproduct and then bury it deep underground. The problem is the capture technology isn't 100% perfect, and you need to have the right geology nearby to store all that carbon. Then, on the other side, you have green hydrogen. This is kind of the dream scenario. You use renewable electricity, say from wind or solar, to split water into hydrogen and oxygen. No carbon involved, period. So what's the catch? It takes a huge amount of clean electricity to do this, which makes it very, very expensive.
And this slide really hits on the core issue for blue hydrogen. Its cost is completely tied to the price of natural gas, which, as we all know, is notoriously volatile. Depending on what the market's doing, the cost of blue hydrogen can swing from just over $1 to nearly $3 per kilogram. So while the tech is mature, it's forever chained to the ups and downs of the fossil fuel market.
Now for green hydrogen. The story is all about one thing, the price of electricity. To be cost competitive, let's say to get under that $3 a kilogram mark, you need a massive and consistent supply of renewable electricity that costs less than $30 per megawatt hour. That is incredibly cheap, and frankly, very few places in the world can deliver that kind of power today. So if blue hydrogen has emission and storage problems, and green hydrogen has cost and energy problems, you have to wonder, is there another way? Well, a third contender is quietly emerging, one that's trying to find a clever path right down the middle. It's called turquoise hydrogen. The process behind it is called methane pyrolysis. Now, instead of reacting methane with steam, like in the gray and blue processes, you just cook it. You heat it to a really high temperature in a reactor with zero oxygen. And what happens is the methane molecule, CH4, it just cleanly splits into two things, hydrogen gas and solid carbon. Notice what's missing. No CO2 is ever created in the primary reaction. Now this is where things get really fascinating, especially where you look at the fundamental physics of it. Thermodynamically, splitting methane just takes way less energy than splitting water. I mean, look at these numbers. Methane pyrolysis needs only about 37.5 kilojoules of energy. That's almost half the energy needed for steam reforming, and it's about one-eighth of the energy needed for water electrolysis. From a pure energy efficiency standpoint, this is a huge potential advantage. Okay, so if the chemistry is that compelling, how do you actually do it in the real world? This is a technology that's still very much in development, but there are a few main approaches being tested right now. The most mature method out there uses a plasma torch. And we're talking about some serious heat here, an ionized gas that's hotter than the surface of the sun. It instantly cracks those methane molecules apart. And this isn't just a lab experiment. This technology is already running in pilot plants and achieving nearly 100% conversion of methane into hydrogen and carbon. A second approach, and this one is really cool, involves bubbling methane gas through a big vat of molten metal. The liquid metal works as both a catalyst and a super efficient way to transfer heat. But here's the best part. The solid carbon that's created is less dense than the metal, so it just floats to the surface, where it can be easily skimmed off. Pretty clever, huh? And that, of course, brings us to the elephant in the room for methane pyrolysis. If you're not making CO2, that carbon atom has to go somewhere. So what in the world do you do with what could be mountains of solid carbon?
It all comes down to this really simple ratio. For every 1 kilogram of clean turquoise hydrogen you produce, you also create 3 kilograms of solid carbon. That is a lot of carbon. So is it a waste product, a bug, or is it something more?
This is where the economics of the whole thing could completely flip. That solid carbon doesn't have to be just waste. It can be a valuable co-product. Depending on the process, you can create things like carbon black for tires, high-purity graphite for electric vehicle batteries, or even advanced materials like carbon nanotubes. If you can sell this carbon for a good price, it could dramatically lower the cost of the hydrogen, turning a potential bug into a major feature.
So, where does all this leave us? Well, we have this whole spectrum of hydrogen production methods, each with its own very distinct profile of pros and cons. So let's just recap real quick. Gray hydrogen uses natural gas and creates a ton of emissions. Blue uses natural gas too, but tries to capture that CO2, making it an imperfect solution. Green uses renewables and water, but it faces those huge cost and electricity hurdles. And then there's turquoise, using natural gas but creating solid carbon. Its biggest hurdle right now is that the technology is still young and needs to be scaled up.
This leaves us with a really fascinating final question. Yes, turquoise hydrogen still relies on natural gas, but it avoids direct CO2 emissions and creates a potentially valuable second product. So could this be the pragmatic bridge technology we need? A way to use our existing gas infrastructure to accelerate the move to clean hydrogen now, while we wait for the cost of green hydrogen to hopefully come down? That's a question the energy world is trying to answer right now.